All right, recording is on. Okay, so today we are going to drill down into an actual use case and look at how we are going to have VTGate handle those. So before that, I just wanted to recap what we did yesterday. Yesterday, we mostly covered example queries and how, from a human perspective, we would have handled it ourselves if we were to do it. As in, like, you look at this query, you say, oh, this is a single shard query, this is an in-class query, this is how we would rewrite it. So getting that understanding was kind of important because then that's how we are going to translate that into our design or code or our approach. So we looked at a few simple routes. The interesting one is this join, is that we have to be able to figure out that this is actually a single shard query, that the entire join can be sent to one shard and that it'll still give the correct results. The next one of importance is figuring out what is a cross-shard join and how we would stitch them up on VTGate using nested loop joins and feeding bind variables from the original query into the second one. And we looked at this awesome rule that we could apply to pretty much most queries, which I call the rightmost rule, which is always use the rightmost query fragment that an expression addresses, and then push that expression into that query fragment, and then use bind variables to actually feed the rest of the values into that fragment. And we looked at the ability that we don't really care whether these joins cascade. It's basically the same code that can handle a single join can also handle cascading joins, because it's pretty much recursion of the same algorithm. So what we did not cover yesterday is basically left as kind of homework to you, or things to think about, is counterexamples. What is it that VTGate cannot handle? The simple answer is if when you break a query up into parts and then and then we stitch them using joins, if there is work left over after that, then basically all those queries are things that VTGate cannot handle today. And right now, if you look at the code, you will see that all those places have error messages. The unsupported prefix in those errors basically say, I don't support this construct, I don't support that construct. So all those places are areas where VTGate figures out that it has to do additional work beyond the join, and therefore it currently doesn't have that ability. And that is actually the clue if you want to implement a new feature or make VTGate support a new construct. That is the area that you have to, that is the place, that's your starting point, basically. Instead of that error, you insert more code to handle those cases. And finally, we also talked about the fact that there is a performance implication to doing joins because of, one, the fact that the data is in different places, and two, the current implementation is kind of simplistic. All it does is iterate one row at a time from the driving table. So those are things that can be improved as needed. After all, it's our code, so we can do whatever we like with it. But right now, we think that it's sufficient it should be sufficient if you're doing standard OLTP load, unless you need to do something super crazy or something that's very, very performance critical and you still need to do cross-shard joins. That's usually the time when you probably need to revisit that code. So when we do the code walkthrough, I can cover that part. All right. Actually, any questions from yesterday that came up after the meeting?
Sounds good. We're ready.
All right. And all right. So this is actually a recap of. So we informally introduced all these operators when we were describing those queries, but this is kind of a recap. So if you say select from an unsharded table, that route we call it an unsharded route. It basically means that the query is just sent to the unsharded database. The other route is if you do a select from a sharded table without a where clause or with a where clause that doesn't have a index, then that's what we call as a scatter route. And yesterday, when we were talking about it, this is basically the relational operators involved in this are basically a route, which is basically a scan performed by the route, and the merge opcode because it merges results from multiple sources. And select a column where ID is equal to 5 is a unique route, which means that it targets a single shard. There is another variant of this route, which is select column where something like a non-unique index is used. In that case, it is a non-unique route. Basically, the Windex given an input yields multiple values, and which may result in different routes being different shards being queried for the same select. We looked at an in clause and how we can actually split this query into smaller parts based on where these in clause values should go. And that's about it. And if you look at it, if you summarize it, the route primitive of VTGate. So basically, a scatter route, basically all routes are one primitive, even though they are semantically different, especially the scatter one. If it is an unsharded route, it is so basically there are depending on what you are trying to do, you may check, oh, am I an unsharded route? Maybe I can send it. If it is a unique equal route, then I can send it. If it's an in clause, so there's various sub opcodes that we may have to check when we decide to do the push down. And then for joins, we have normal and left joins. So these are the only primitives that we are going to start with. So this should be clear if you have been in the previous two sessions. So here is a simple use case. I have a query here that selects from two tables, and the join is not on a sharded column, sharded index. And there is actually a where clause which has a constraint on a sharded index, but it's only on the first table, the table A. And on the right-hand side, we have the tree that VTGate will build as output when it sees this query. So because the join is not on a sharded index, it is not a single route query. So therefore, we build two routes. So this is the left-hand side route handles table A, and the right-hand side route handles table B. And if you push all the components of when I talk about push, it's actually a term you will see me using quite often. It is basically pushing elements of the query, of the original query, into the route. So that's basically what we call as pushing. So I push elements of table A, elements that reference table A, into the left-hand side route, which is a.id, a.a1, from A where a.id equal to 5. But then we realize that we have a new dependency that we introduced because of the join. Therefore, the original select needs to also export a.n because that needs to feed into the second query. And the second query is what is left over from the original query, except that the equality of a.n is equal to b.n is rewritten as b.n equal to colon a underscore n. As you can see, we have played around with the ordering. Ideally, it would have been colon a underscore n equal to b.n. But someone said that MySQL doesn't like that construct, so we actually flip it. So beyond this pushing, if you look at the route description itself, because we have multiple types of routes, we need to identify what type each one is. In this case, it's an equal route, and it uses IDX, which is the Windex for A for column ID, and the value for the Windex is 5. So this is basically your left-hand side plan. And the right-hand side plan says it's an equal clause. So basically, I think I'm implying that n is name, which means that it's a non-unique route, but it's still an equality route. It is on the user key space. The Windex is now this time name, and the value is a.n. And actually, it should be a underscore n. So I need to fix that. And now these two are joined, and the join condition says that you need to take column number 2 and build a bind variable called a underscore n. Column number 2 from the left-hand side result. That's what the 2 stands for here. And finally, join says that you need to you also need to specify to join what results have to be returned from each of the routes. So from the left-hand side, you need L0 and L1, which stand for a.id and a.a1, and R0, which is column 0 of the right-hand side route. So this is clear? Any questions?
Yeah. So on this one, do we execute? I may be going forward a lot, but do we execute the left route and the right route in parallel? As to so for example, do we execute right route without any where condition, and then at join we filter based on a underscore n, or we execute the left route first and then give the right route where condition clause?
We do the latter. Basically, we execute the left-hand side query first. And for each of the rows that come out, we actually build the bind variable called a underscore n based on the result that we received, and then do a loop actually. For each row that we received from A, we loop on the right-hand side and then fetch the results. And for each row that we get from B, we actually combine left and right and return the row.
Okay. But
so that is so basically we do as the relational operator describes the operation should happen.
Okay.
And
got it.
Yeah, and we have, as I said, we have room for improvement. We could, for example, fetch a bunch of rows here, and then do a combined
streaming approach. Okay, got it.
Yeah. So that is, so basically, right. So basically, this is basically our first. This is basically join V1, and it is focused on correctness. And so we can now focus on optimization based on the reason why I haven't done any optimization is because I'm waiting for people to start using it and see what kind of problems they are facing, and then we can try to address that on a case-by-case basis.
To that point, what kind of metrics should we build, rather not build, but should we look for, especially for these use cases? Because we definitely need to see the latencies on VTGates.
Yeah, at this point, I would say use the total latency of a query, right? That's your bottom line cost.
Okay, right. Okay, got it.
So if that is unacceptable, then we can go and see what can be done.
Right. Okay. All right. Cool.
Yeah. ultimately, if the data is in two places, you have to read them in those two places. So there is an unavoidable cost to joins, to cross-chart join. So the only thing we can do is optimize the number of round trips and the number of queries we issue to fetch that data.
Mhm.
Cool. So now that I've described what is point A and what is point B, we are now going to go through an exercise of actually going through the journey, how we go from point A to point B, which is hopefully be the next slide. Oh, not yet. So before, actually, it is the next slide. This is the first step of going from point A to point B. Is when you receive a query, the first thing we do is parse it and build an AST. And the right-hand side is the AST representation of the original query. The notation I'm using here is I'm using fixed locations in the oval to signify different parts of the query. So basically, the bottom of the select is your from clause. The bottom right is your where clause. The top right is your select expression. And the left-hand side are all the post-processing expressions, which is group by, having, order, and limit. So, because I'm using this location, I don't have to specify that this is the from clause node and this is the where clause node. You can infer that by just looking at where in this circle the node is attached. Does that make sense? All right. And there is also a reason why the nodes are like this. This basically means that when we analyze a query, we start from the bottom, which is the from clause, and go counterclockwise all the way to the end. So we analyze the from clause first, and then we go to the where clause, and then we go to select expressions, and then group by, having, order by, and limit. So that's basically our order. So the first step we are going to do, so as I said, we are starting with the from clause. This actually is a query that is joining on a unique index. As you can see, it is the join condition is a.id equal to b.id. And when we start walking the tree, we go to the from clause. Oh, it's a join. Oh, let's see what's on the left-hand side. It's a table A. Now, actually, looks like I've skipped a large number of steps in this slide. The rule we are going to use is, if you look at a query and you look at just from A, right? We are now looking at the construct called from A. So the from A construct is equivalent to select star from A, right? It is basically scan all the rows in A. That is the only thing we know about that query. We know that the query can potentially have to look at all the rows in table A. So what that means is that we can provisionally build a route for that subsection of the query, which is basically the route 0 is what we call here. It is basically a select statement that scans all of A. And because it scans all of A, the route opcode is scatter. So just by looking at the from clause, we already have a potential plan for the query that we are going to build. That makes sense?
Yeah, that makes sense.
And then we say, okay, we've built route number 0. Then we go, oh, it's a join. So I encounter B. Oh, it is from B. So I need to build a route for that B. And it's identical. It is also route 0. And the reason why they are both 0 is because they don't know about each other yet. So the route numbering is basically the execution order. We start with route 0, go to route 1, route 2, route 3. And those routes are numbered based on the joins that actually put them together. So these two routes their numbers will be changed when they come together on a join. And the reason why these are both route 0 is because the algorithm is inherently recursive. And so we are basically, these routes exist in different parts of the recursion, currently unaware of each other. It'll become more obvious when you look at the code why this is straightforward. And then what we are going to do is, we've looked at the route. Now we are looking at the on clause. Oh, the on clause, it says, this is a single route. These two tables can be together in a single route. And this is what it becomes. So now what I've done is I've rewritten my select AST, and this entire subnode, the join A, B, and A.id equal to B.id is pushed down into this select. As you can see, this is valid. As you can see, the opcode is still a scatter. So basically, this is from A join B on A.id equal to B.id, and that is actually a valid route. It's a valid scatter route that actually goes to all shards. Remember, we looked at a query where there was a join with A.id equal to B.id with no where clause, and we concluded that that's a valid scatter route. So that is basically what this has become. So far, so good?
Yep.
So what we are basically trying to do is start with the from clause and go around this tree and attempt to push as much of these SQL elements down into the AST that a single route may contain. And if at the end we manage to successfully push all of them, our job is done. So far, so good?
Yep.
And so I'm going to skip beyond this because the next step is going to cover the use case where the join is not on a single index, and then what happens there. And then we'll continue the story of what happens to the where clauses beyond, which actually the story becomes kind of the same in scenario 2. So in scenario 2, it is same as scenario 1, except that the join condition is on a non-unique, oops, I accidentally clicked, on a non-unique index, which means that the join cannot be pushed down into a single shard. So just like before, we had built R0 and the two different routes. But when we look at the join condition, we say, oh, okay, this cannot be in the same shard. Therefore, this time we are not going to merge the routes. Instead, we are going to build a new opcode called join. And it is going to join R0 and R1. So this is still a valid, a semi-valid opcode, because what we are saying is that select all tables from A, and for each row that comes out of A, select all rows from A. And for from each row that comes out of A, select all rows from B, and then join them and then return the results. And of course, this is a super inefficient plan, but it's a valid plan. So the next thing we are going to do is analyze A.n equal to B.n. And we are saying, oh, okay, so this is a, and what are we going to do? We are going to apply the rightmost rule. A.n equal to B.n means that this on clause needs to go to the right-hand side. And so that's what we did, because B is referenced here. Okay. But as soon as we, so there is another change. In this case, it is an on clause. And but when we pushed it down as a where clause, because on clause is applicable only if you're a join. So it is necessary that you convert that on clause to a where clause here when we push it down. There are actually scoping rules that you have to be careful about when you convert an on clause to a where clause. I believe there is there must be a slide that talks about it. I think we'll talk about that when we come to the symbol table. So you should be careful when you cannot always indiscriminately move things around. But in this case, I believe I went through the waiting process and then concluded that it is safe to convert a non-class to a where clause. And as soon as we push a constraint down into a route, the next thing we have to do is what? Is see if that affects the route, right? Now that we have a constraint called a dot n equal to b dot n, and we know that n actually has a index, we go and say, let's change the route here and make it an equal route that uses the name index, which means that we basically improve the route on the right-hand side. Now it's basically using a index. So we do that for every where clause that we push. As soon as anytime you push a where clause, you go and see if that where clause has a potential to improve your plan. The next thing we do is we push a.id equal to 5. If you use the right-hand side rule, obviously it only references table A, so therefore it's safe to push that into the left route. And as soon as you push a.id equal to 5, that plan has improved. And now that's become an equality plan using the IDX index. So far, so good?
Yep.
I think silence is good.
Can you hear us?
Yes, I can hear you.
Okay, cool.
And so now we have done the from clauses, we have done the where clauses. Oh, we are making good time. Now we have the select expressions to deal with. So same rule. Select is actually the easier part. Is you go to as long as they are simple expressions. If they are simple expressions, all you do is apply the rightmost rule and just push it down, 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 down. Oh, not just push it down, because of the fact that when you push down, it is necessary for the join to know what to return, right? Because it is joining two tables, it needs to know the column numbers from the left query that it has to return back to the application. And the reason why it has to know it cannot return blindly all column numbers is because, as we saw before, we are likely to add more columns to select statements. So the join has to know what to return and what to ignore. So we push a.id and a.1 down to the left-hand side. And we also mark saying that left 0 and left 1 need to be returned back to the caller. And then we push b.1 down to the right-hand side. And we add here saying that R0 needs to be returned. We are almost home free. Now all that is left is the stitching. This query would not run as it is. The reason is because we still have this red spot here where this query on the right-hand side is referencing an a.n. And if you just gave it to this route, it's going to say, I don't know what a.n is because it's not part of this query. So then we go look for external references in each of the routes. And if we find an external reference, then we say, we need to go find out where it's coming from, and then go ask that guy to supply it to me and pass it up the tree, and then build a bind variable that will then pass it down to me, which is what we do. Yes?
Is this the wire up phase in the code or no?
Yes, it is the wire up phase in the code. Okay. And there is actually a lot of thought that went into that as a phase, because there are many options, right? One option, for example, is hold on, is to do it at this point itself, right? You could say, as soon as I push it down, I already know that a.n is foreign, right? I could have immediately said, let's get it from route 0 right now. Why wait till the wire up phase, right?
Yep.
There is a problem with that, and we will cover that. It would work in this particular case. So you could have immediately said, okay, let's immediately wire up a.n, put the bind variable, add that a underscore n here, and do everything here, and then push the select clause. But there is a problem with it, and we will come to that once we gain full understanding of the rest of the algorithm.
So I have a question.
Yeah.
So this query that you're going through doesn't have any like group by, having, order by, and limit. We're all like
Correct.
missing. But order by and limit, I guess, like together, and certainly having, could also affect the route, right? That could also improve it from a scatter to something else.
Yes, yes.
Is that
So the way we do it is, the way we can determine that is we just keep going around.
Yeah.
And when we come to the order by, we look at the current plan that we have and see if we can push the order by down into one of these routes or all of these routes, whether it even makes sense to push it down, right? And if it makes sense to push it down, and if order by does in fact improve a plan, then yes, it will improve the plan. But right now, there is no plan improvement possible with order by for VTGate. It will improve the MySQL plan.
On the contrary, if you have an order by and limit, that is like if you're ordering by the, I think what's the right word, V index.
Okay.
And you're limiting, you could actually be like limiting to a certain part of the sharding range.
Yeah, but that is so right now that is actually one constraint, one limitation of a V index is that there is no assumption of an order for V index.
Oh, I see, because it's like a hash or something.
Yeah, it could be a hash, it could be anything.
I see.
But we have talked about V index as being range aware, which means that you can say this index is a rangeable index, like those that are identical. And then if that was the case, then we could obviously handle inequality.
Yeah.
We could handle order by, but we don't have that yet.
Okay. Maybe the same thing with a having.
Yes, having actually can and will improve the plan.
Okay.
Because if you have a having clause that is actually putting a constraint on a index column, we can definitely use that to improve the plan.
Cool, thank you.
And I think I do. I'll have to go check the code. So finally, the wire up happens, which is the actual algorithm is go looking to your left and find, actually, I don't think it goes that way. Yeah, actually find out where a.n is defined, and then find a common join node between those two routes. And then from that join node, go down on the left-hand side, asking each subnode to supply a.n. And that goes all the way to the route, and the route will say, okay, here's a.n. And then once the join has obtained it, it will say, I think it's called procure. Yeah, the word is called procure a.n from the left-hand side and supply it to the right-hand side, which is a_n. So that's basically the wire up phase. So as you can see, this explains why you need this list here, because now the left-hand side is actually returning all three columns, but only 2 of those are going to be returned back to the caller. This is good. So far, so good. Fully understood?
Yep, we got it.
Yes, that's
all right. This is awesome. Like the last time I tried to explain this without going through the introduction phase, I think it took me 3 hours just to explain this. I think it's now very straightforward because we covered all the prep material. I want to see if there is anything else of importance that I could have missed here. I can't think of anything. This is all there is to it.
I think it does help a little too if someone like reads the code a little bit. Like it helps to have some of the context of having like looked at the code and not fully understood it.
Yes. I guess that's why. So now comes the twist in all of this, which is the symbol table. So all this is nice and fine as long as it's a simple query and you can search stuff. But when a query starts to get joins and subqueries, and if you start if you start breaking queries up into other parts, you have to make sure that you don't break any of the SQL reference rules, right? Like, for example, in this position itself, I am breaking this query up into two parts. I have to make sure that a reference, when I break it up, a reference doesn't accidentally point to something else. So all those rules have to be honored and preserved. And for that, we need actually a symbol table that basically uniquely identifies each reference that items of an AST to make sure that we don't forget what it means. So the symbol table rules actually, unfortunately, are different for MySQL than standard SQL. And that has led to quite a bit of confusion. I think after much peer pressure, I have succumbed and now switched the symbol table rules to follow MySQL, even though it's not standard SQL. So actually, I don't even know if I updated this slide for that. So here are the rules. Actually, what is the goal of the symbol table? It basically gives you, it basically ensures that all access is validated, which means that if you're referencing a table, it makes sure that the table exists. If you're referencing a column, it makes sure that the column is part of the table. Obviously, we don't do it, and I will show you how we do that because we don't have the schema information. But definitely, if there is a Windex reference, we recognize that. And if you look at the previous thing, and you walk around and you look at this a.id, for example, and you ask, oh, where is this coming from? You always want to ask the question, where is a.id coming from? You need the ability to say that a.id comes from route 0. And you need to be able to say, where is b.n? b.n is in route 1. So that's a question that the code needs to answer, especially for the stitcher, for the wire up phase, right? We saw an a.n reference here, and we have to ask, where is that coming from? So that's a very important question that a symbol table has to help us answer, which is the get route. There is a caveat here. Get route is actually a cheat. It assumes that all symbols are produced by a route, which actually will not be the case when we go full relational, right? Because a symbol can be built by an intermediate step within VTGate itself. So this get route will someday has to become a get primitive, which means that tell me the primitive that produces this symbol. So that is something of a shortcut that I used that will have to be revisited when VTGate starts to handle more primitives. But right now it's true because the only items that produce symbols are routes. And then it tells you which Windex, and we use that in the wire up phase. So the symbol table rules are as follows. Inside a from clause, no correlation is allowed. So if you are, what that means is that you cannot reference anything in the outer query from inside the from clause. Actually, I think standard MySQL allows, but for whatever reason, MySQL decided not to support it. So well and good, no problem. In the case of an on clause, only the participants of the join are allowed to be referenced. So you cannot say A join B. You cannot say A join B on C dot something and then have an on join C later. So the on clause always references what's on the left-hand side of the construct. And if it is parenthesized, it's only what's inside the parenthesis, not what is outside. The where clause can only see what is coming in the from symbols. So often, if you write a query where select A from B, where A equal to 10, that A is actually not referencing the A that's in the select expression list. It's actually referencing what's in the from clause. It's a subtle difference, but it's actually important, and we'll come to that later. And obviously, it can reference any symbols of the outer query. If you are in a subquery and you are in a where clause of a subquery, it can reference the symbols from an outer query. So here itself, there is a huge complication. Which part of the outer query are you allowed to reference? Are you allowed to reference what's in the select list of the outer query, or are you only allowed to reference what's in the from clause of the outer query? Right? And the answer to that question is, the simplistic answer is, well, whatever is allowed by the outer query in the context in which the select appears is what you're allowed to do. So in other words, if you say select star from, select something from table A where, and then you have a subquery in there, that subquery cannot reference expressions that are in the select list of the outer query, because the subquery is in the where clause of the outer select query, and by the fact that the where clause cannot reference items of the select list, you cannot reference those in your subquery. Does that make sense? That's a lot of words. I might have lost some of you while I was explaining this.
Why can you not reference in the where clause? You can only reference from like it's valid SQL, right? To do like select A from foo where A equals whatever.
Well, here's the place where it won't work. If you do a select count star and try to reference that count star in your where clause, you will get an error.
Gotcha. Yeah, that makes sense.
So that is actually the proof that you are not allowed to reference anything in the select list in your where clause. And that applies to any subquery that you write inside the where clause also, basically.
Yep, that makes sense.
Yeah. The confusing part is that the subquery itself has its where clause. And so the scoping rules that you apply for resolving symbols in the subquery's where clause change when the search leaves that subquery and goes to the outer query. So basically, you may have 3 levels of subqueries, and each time you leave the context of a subquery, the rules of search change depending on the context of the outer query.
Yeah, your scope diminishes.
Yeah. So you could have a subquery in a having clause that has a where clause, or you could have a outer query that has a having clause and a subquery inside that has a where clause. And the way you search within the subquery has to use the where clause rules. And if you come out and you're in the having clause of the outer query, you have to use the having clause rules for searching in the outer query. So basically, you cannot say, I'm in a where clause, so I'm going to apply the where clause rule everywhere. The rules have to change as the scope changes, which is very, very confusing, but surprisingly easy to implement in code. I will show you. But there is it actually dictates a very specific design about how to implement symbol tables. And if you follow that design, then it's a very, very brain-dead code that implements these things. The reason why I'm showing the complexity is because I went through this pain of learning this and realizing, oh, okay, it looks like we need a very specific design. And I will talk about it. I think the next slide will cover it. If it doesn't, I will cover it right here. So same thing in the select list. The select list actually has one difference. Select list can only reference from symbols, and it can reference the outer query. But at the end of your select parsing, you produce new symbols. And those symbols now become visible to the rest of the query constructs, which we call the post-processing part of the query. Post-processing are group by, having, order by, And all those constructs are allowed to reference items from the select list. So there is something really, really unfortunate here. I have no understanding why MySQL did what it did. And I probably will, somebody will someday enlighten me as to why it did that. Which is when, and actually I did not implement it in our parser about how it resolves symbols, but I'm saying here because someday it could cause some confusion. I don't even remember the rule, but when MySQL resolves a symbol for, I think the order in which it resolves symbols is different for a having clause versus an order by. I believe in the case of an order by, it goes to the from clause first and then select clause next. And if it is the having, it goes to the select clause first and from clause next. And I have no idea why they did that. That is, standard SQL doesn't require you to do this, and making this an expression just doesn't make sense at all. My guess is that there is some use case that dictated this change of behavior, but they did it, and that is the case. In most cases, these are not really that significant, but I have a feeling one day this is going to come and haunt us. So I'm just saying it right now that this quirk exists in MySQL. I only know it by reading their description of symbol resolution. I actually haven't looked at the code to verify whether this is actually the case.
So another thing is available during post-processing in MySQL. This is like this well-known MySQL quirk. You can, for example, select ID from A, group by B, where you're not actually selecting for B.
Correct. Yes, and that is now allowed by VTGate by the fact that when we search the symbol table, if we don't find it something in the select clause, we go look for it in the from clause.
Okay.
So earlier I never used to allow it, but I recently changed that behavior so the way V3 works is it always looks at the select clause first, and if it is not found there, it searches the from clause.
Okay, thanks.
Yeah. So most sane queries should work fine, basically. And searching in the from clause first and then the select clause next, I actually don't. I don't think it's really material, but it's probably material in some. There's probably some use case where it's material, but usually it shouldn't matter because of the fact that applications usually try to write readable queries because engineers have to understand them, so they try to naturally avoid such ambiguities. So we have human nature working in our favor in this case. Basically, if somebody writes a query that, if you write a query that I don't understand, I will throw it back at you and say, can you make it understandable? Because I don't know what the behavior it is, but make sure that the query is more explicit about what it should do, right? So based on the fact that our human brain wants to look for simple things, it's usually applicable. All right, so let's see what the next slide is. Oh.
Sugu, we'll be leaving. We have a different meeting.
Oh, we are almost out of time. I could actually, let's see. Yeah, what I'll do is I will finish this design. Yeah, you can leave, but I'll finish this design slide and then end here. And cool. We can go into the symbol. We have already covered what I felt we should cover at least today. So cool. I'll just finish with this slide.
Cool. Thanks a lot.
Thank you.
Have a good one.
So the symbol table design that we are going to follow is so if you look at if you go back here, there is actually method to the symbol table madness. These rules look actually very, very weird by the fact that why is that from class can only see this? Why is this limitation on the on clause? Etc., etc., right? And actually, there is a reason why these rules exist. It's because of our parsing order. So when you build, when we were analyzing this particular AST, right? What did we do? We started with the from clause, looked at each table, and then we analyzed the on clause. And when we looked at the on clause, we validated it against the tables it was referencing. Then the where clause, then the select list, and then the post-processing. So basically what the design is dictating is build your symbol table as you analyze your query. So that's basically what it says. It says when you see A, build a symbol table for build a symbol entry for A. When you see B, build one for B. And then when you look at the on clause, you will only have A and B. And so if there is any reference here that does not reference A and B, it's an invalid reference. And after this, you go to the where clause, and the where clause will be allowed to reference all symbols in the on clause. And then you do select. Select also references symbols from this area. But at the end of select, we create new symbols. And once we create those new symbols and add it to the symbol table, then automatically the rest of the constructs will see what the select clause produced. So that is actually the reason why the symbol table rules are the way they are. They are basically the design is dictating that you build your symbol table as you analyze your select, and there is a very specific order in which you have to analyze your select. And if you follow that order, you don't have to actually build any special code to handle the symbol table entries. So that makes sense?
Not really in terms of looking at the code, right? The symbol tables aren't built up at parse time, right? I thought it was like after.
Yes, they are. Yes, parser actually goes left to right. So parser builds the select first and the from later and the where clause later, right? But our analysis goes from clause first, where clause on clause next, where clause next. So it's more in the order in which we analyze the SQL, not the order in which the AST is built.
Yeah. Okay.
So basically, this exact thing that we hold on.
And
so
when
when we went through these motions, right? The order in which we built this plan is the order in which the symbol table is built.
Yeah, and when you say analysis, it's the plan builder.
The plan builder, yes. Yeah. So the order in which we analyze for the plan building, or the order in which we build the plan. We look at the elements to build the plan. So a symbol table is created for every item in the from clause. And when the symbols merge, which is when the routes merge, we combine the symbols of the symbol table into one. Until then, they are separate symbol tables. And the reason why it is important to have separate symbol tables is because that from clause could have a subquery in it, right? And in that case, the only symbol that subquery can see is that item in the from clause. So it's all naturally falls in place if you do it like this. We build only one symbol table per select statement. And because there are scoping rules, every subquery will have its own symbol table. And a symbol table that is in a subquery will have a parent symbol table. Because if a search within a subquery symbol table fails, it needs to search the parent. And but each symbol table has its own state, which is independent of its parent or child, which means that when a search ends in one symbol table and is continued into another symbol table, the current state of that symbol table is used, which means that if you are in a having clause in one symbol table, then that part of the search will look for the statements in the select also. But if that subquery was, again, that query was itself a subquery of another outer subquery, that symbol table may be in a different state. And the resolution order is always select expressions if present, then search the local tables, and if those two fail, go to the outer symbol table. There is actually one final thing that the symbol table has to give us, which I will explain later when which will become more clear when we look at what we do with the symbol table, which is it needs to track all external references. So basically, if a search fails within the local symbol table and that symbol is searched outside of the current symbol table, then the local symbol table needs to know that this reference was resolved externally. And the reason why that is needed is in order for us to apply the rightmost rule. So basically, if we say where clause and then there is a subquery in there, and that subquery, let's say, is correlated, and then that subquery referenced something in the outer symbol table, then we need to know where to push this subquery, right? And we have to push this subquery to the correct route only if we know what is the rightmost route, the symbols of the subquery referenced in the outer query. So that's the high-level description of why we need to track external references. It will hopefully become more clear when we do the drill down. And that concludes our session for today. And tomorrow, we will redo the same exercise that we went through today, but this time we will look at what happens to a symbol table as we build the plan. So that's basically what we're going to do tomorrow.
Great.
So,